Welcome to our lecture on the M3-N5 theorem. Imagine you are a building inspector checking a newly constructed house. Instead of testing every single brick, nail and wooden board, you just look for a few specific defective parts. If they are missing, the house is sound. Today we will learn how this exact same logic applies to mathematical structures called lattices. Before we dive into the theorem, let us understand what a lattice actually is. A lattice is a mathematical set where any two elements have a unique least upper bound, which we call a join, and a greatest lower bound, which we call a meet. You can think of a lattice like a family tree. Any two relatives have a closest common ancestor, representing the meet, and a closest common descendant, representing the join. This structure keeps everything perfectly organized. Now that we know what a lattice is, let us talk about a special, highly organized type called a distributive lattice. Here, the join and meet operations distribute over each other, just like multiplication distributes over addition in basic algebra. The M3-N5 theorem gives us a powerful shortcut. It states that a lattice is distributive if and only if it does not contain a hidden diamond shape known as M3 or a hidden pentagon shape known as N5. Let us visualize these forbidden shapes. On the left, you see the M3 lattice, shaped like a diamond. It has a bottom element 0, a top element 1, and 3 independent middle elements. On the right is the N5 lattice, shaped like an asymmetrical pentagon. It has a chain of 2 elements on one side and a single element on the other. If your mathematical structure contains either of these hidden shapes, the distributive rule breaks down entirely. To truly understand why these shapes are forbidden, we must look at the distributive law itself. This formula requires that for any three elements, taking the join first and then the meet must equal taking the meets first and then joining the results. The wedge symbol represents the meet or greatest lower bound, and the V symbol represents the join or least upper bound. If a lattice is distributive, this equation must balance perfectly for every possible combination of elements. If even one combination fails, the entire structure is non-distributive. Before we prove the theorem, let us see this with a concrete example. Consider the lattice formed by the positive divisors of 30, ordered by divisibility. We want to determine if this lattice is distributive. First, we list our elements 1, 2, 3, 5, 6, 10, 15, and 30. In this specific lattice, our join operation is the least common multiple, and our meet operation is the greatest common divisor. We will use these operations to search for any hidden forbidden shapes. Let us test a subset of these elements to see if they form a diamond. Taking 2 and 3, their least common multiple is 6 and their greatest common divisor is 1. If this were an M3 lattice, we would need a third element, say 5, that also joins with 2 to make 6. But the least common multiple of 2 and 5 is 10, not 6. By exhaustively checking, we find no diamond or pentagon shapes. Therefore, this lattice is perfectly distributive. Now let us look at a case where the distributive rule fails. We are given a lattice with elements 1 through 6. The bottom element is 1 and the top is 6. Elements 2, 3 and 4 sit directly above 1. Element 5 sits directly above 4, creating a chain. To prove this lattice is not distributive, we do not need to test the formula on every single combination. We just need to hunt for a hidden pentagon shape within these connections. We extract a specific subset of 5 elements 1, 2, 4, 5, and 6. Let us verify their relationships to see if they match the pentagon structure. On the right side, we have a chain where 4 is strictly below 5. Now we check the left side, which is element 2. The join of the left element 2 and the lower right element 4 is the top element 6. Similarly, the join of 2 and 5 is also the top element 6. To complete the pentagon, we must verify the meets to ensure they all connect to the same bottom. The greatest lower bound of 2 and 4 is the bottom element 1. Finally, the meet of 2 and 5 is also 1. Because these 5 elements perfectly mimic the structural relationships of the pentagon lattice, we have found a hidden N5. According to the theorem, this instantly proves the entire lattice is non-distributive. Now that we have used this theorem to inspect lattices, let us mathematically prove why the diamond lattice, M3, destroys distributivity. We are setting out to show that the distributive law completely fails for this specific shape. We will test the distributive law on the 3 middle elements, A, B, and C. Starting with the left side of the equation, we first evaluate the join of B and C. Looking at the diamond shape, the lowest point above both B and C is the top element, 1. This gives us the inner part of our left side. Next, we substitute this result back into the left side of our equation. The meet of A and 1 is simply A itself because A is below 1. Now, let us evaluate the right side. The meet of A and B is the highest point below them, which is the bottom element, 0. Similarly, the meet of A and C is also 0. Joining these two zeros gives us 0. The left side evaluated to A, but the right side evaluated to 0. Since A is not equal to 0, they do not match. This proves the distributive law fails completely. You might wonder why this theorem matters in the real world. In computer science, logic design, and database theory, distributive lattices are essential because they allow us to simplify complex Boolean expressions safely. If a system's underlying logic forms a non-distributive lattice, applying standard simplification rules will lead to catastrophic errors, like a circuit outputting high voltage instead of low. This theorem gives software compilers a fast, visual way to verify if a logic system is safe to optimize. Let us summarize what we have learned. The M3-N5 theorem is the ultimate diagnostic tool for lattice structures. It proves that the failure of the distributive law always leaves behind a specific structural footprint, either a diamond or a pentagon. By ensuring neither of these forbidden shapes exists within a lattice, we guarantee that the entire structure behaves predictably and follows the distributive property. You now have the tools to inspect any lattice with confidence.